They care where they are. They can't. Please, hello. Let's try to do it together. Please, God, should you understand that we should not do anything special when we write this? What we just do is the formula we have for kinematics, we write it, but just use the terms that are associated with several relationships. That's what we do. Nothing special. And let's not look at that book. Let's try to look at the process. You have the formula now, so I can clean it. I want to clean it. Everything we do. I need the question, please. Please, class, 1, 2, ready, go. Are you there? Yes. So we should not solve it. Yes. No, let's solve it. So help us now. A gramophone. Okay, 2 seconds. Constant angular revolution per angular so I think that what is constant. Is that all? And the number of revolutions. And the number of what? Revolution. Is that all? Yes. Yes, so. Okay. So they say gramophone record. There is nothing here. The only problem that you have is just the conversion. That's just it. So I will say anytime I want to convert, or anytime I'm giving you a revolution per minute, remember that I said we don't use revolution per minute here. What we use is pi, and pi is radians. Then seconds for our time, not minutes. So I will simply say the 60 revolution per minute is something like this. I remember when I taught you how to convert. I told you that you will always say 1 minute is equals to 60 seconds. Right? Yes. Then I will put it in such a way that minute will be the way that to pass 2 minutes. So I will say times. So I will say 1 minute over 60 seconds. It's like in the family, you are the one that are spoiling. Because I know your sister will always be active. In fact, you are supposed to be staying here. Yes. So I will show you how to do the work. I like acting stuff. Sister, because she will come outside. For her. Go and stay here, sister. So you will see angelic spirit of God. I will go in the class. No, maybe I'm not the sister. Yes. I will do that here for class. Before they register you, that thing will call you for class. So, yes, we need to make sure that all the sister. And our sister is very sharp. I still know. That should be 400 now. I see. You can see that this one is listed. I have many to cancel many, but notice that I have revolution here, should be? Yes. And I will say, one revolution is equal to how many? 2. Hope you know that this thing means pi is 1/8. 1/8 times 2 is 3/6, and 3/6 is for a circle. So I'll have the times. I'll put revolution here to cancel revolution. So I'll say 1 revolution is equal to 2 pi. So revolution revolution, cancel revolution. Minutes can cancel minutes. This 6 we can cancel this 6.
Yes.
I see it. So you see that I'm left with just 2 pi. You see how to
Yes.
And notice something. Notice something. Notice that this thing that I have here is 2 pi. You see how to write it table doing That's what something. What I have here is 2 pi. You see how to then notice that revolution per minute or revolution per time is frequency. Are you aware? So this is frequency. I see it. Now, I did remember I put this one for conversion reason. So you can see that whenever we are trying to do this, we always cut across that about 2 pi f. Just that the arrow did not enter because we're not thinking about this. So if I know this, it's simply going to teach you that anytime you want to convert from revolution to pi seconds, radian seconds, all you need to do is to simply be putting it in such a way that whatever you have, this part will cancel this part. Whatever you have this part, you'll be able to cancel this part. So I'm left with just pi. And notice that there's second here. Since I do not cancel, so I have 2 pi over seconds. And this gives me radians, rad over second. See that? And I know that the thing that has rad per second is simply angular velocity. Do you remember? So my angular velocity here is going to be 2 pi per second. So 2 pi is equal to 2 pi per second. Now let's go again. They told me something about from rest, which means my initial angular velocity will be very important. The same concept with kinematics. The same concept with kinematics. The same thing. The only thing is just that they will put in certain things like revolution to confuse you. But it's the same concept. If you know kinematics, you know this one. Just the same concept. So then I'll say W is equal to 0. And another thing I want to teach you is this. Whenever you see a question, maybe they said something happened, a body attended the emotion, and this one happened. Before you start thinking of how to use that formula, those individual formulas I gave you, like displacement equals to acceleration equals to velocity equals to, before thinking of it, first of all, think of equations of motion. Can you hear me? Before thinking of using all those individual equations I gave you, that one is maybe, they give you a question, they just come and tell me, even it's not a long question, it's not a question that involves a body moving or whatever. Direct questions, I can easily use those normal individual parameters to find it. But when they start giving me long things, something that happened, like telling me stories that involve what happens in emotion, emotion, the first thing I need to always think of is equations of motion. So that it will be easy for you, because I know what you are confused with is you have a lot of formulas now. Then you are not asking yourself which one to use. If you use it well, they will always give you the same answer. But to make this easy for you, always think of using equations of motion. Once you see that there is a story to that motion, So when I say, looking at this, they said from 0 years, then they said it's my first year. Time. Okay, they give me time. They give me 2 seconds, you mean? Now, once they give me this, I'm complete. So I can now say, if I don't have alpha, or you say acceleration, if I don't have this, I can easily say that there is an equation of motion which gives me W plus but if I want to use a no problem, should I told you? So I will say my W is what? 2 pi. You see that too? My O is 0. Then my A I don't know. Then my T is what? 2. Now you notice that if this thing do this thing, you might just do 2 alpha. Or then, in fact, I want to be using the so that some people don't run. Okay, so alpha. 1, 2 alpha. Then I have 2 pi. Now you see that easily. This thing will be the same thing I say to make acceleration solid of the formula. But please write this somewhere, note that this is acceleration. So divide both sides by 2, divide both sides by 2. This will cancel this, so that acceleration is equal to this will cancel it. It's equal to what? Pi. You see now? Yes. And you know that if that be the case, remember that acceleration is always in radians per second square. Do you still remember? So instead of saying meter per second square here, we are using radians per second. Everything about kinematics, the only thing is that instead of meter, we are using radians. Here, it will be the same. And I told you, once a particular question of motion start telling you a story, what happened here that this one happened, know that you first of all be thinking of equations of motion. You did what? No, never. No, never. We have v equals to u plus at. That is what we use. Then we have s equals to ut plus half ac squared. Then we have u squared equals to u squared plus 2as. So that is the equation we use. Correct. I asked. No. See, yes. Now notice something I said. Find the angular acceleration. Assuming that it is constant. Assuming that our acceleration is constant. Now they said to reach its constant angular velocity, they give us a final velocity. Now they are still telling us to find its angular acceleration. And remember that what we are doing here is acceleration, not linear motion. So whether you like it or not, it's just for example, even if, let's put it this way, even if the velocity is constant, for the fact that that body is rotating, in fact, anybody that is going through circular motion, unless it's speeding up or slowing down, but for the fact that it's going through a motion, whether the velocity is constant, acceleration must be there. Without the acceleration, it will not maintain that fixed path. So, thank God you asked me that question. In linear motion, when velocity is constant, we know that acceleration is zero. But in angular motion, once a body is rotating, even if velocity is constant, acceleration will always be there. Because it has to be turning, and if it's turning, that means acceleration is there. There's force, centripetal force, and the centripetal force is there, centripetal acceleration is there. The minute the acceleration is there, to start going straight. It's no longer there, so you need to do that. That's why we calculate that for acceleration. Alright, then they asked us to find what? The number of revolutions it makes before it attains the speed, Jamie? Alright, before it attended this speed, which is, here's our W. Yes. Yes. This is W, Shemi, 2 pi per radian second, Shemi. That means that if you are checking it, it's actually in 2 pi. This is just our number of revolutions made. So just 2 pi radians. That's just, and I hope you know, see, I hope you know that the unit of theta is radians in physics, circular motion. And yes, we know that angle, there is a common belief of using the unit, right? But the SI unit of angle is radians. I've said it before. That means that if they ask me the number of revolutions it makes, they are asking me how many radians. So I'm going to just have 2 pi radians. So I'm going to just have that this is going to be 2 pi radians. Give me the history of this before doing anything. Because from here I get 2 pi per second. This is for velocity 5 per second. But the answer here is just this one. Those equations. Alright, so let's move to the second one. It's not confusing. It's not hard. It's just all these little things I normally say before solving. That's where the understanding lies. Once you are remembering all these things, like for example, this one I just said, once the question is telling you a story, it's best to think of equations of motion before doing all those individual formulas. That will save you a lot of stress. Because some people, once they see a question, and because they don't know how to derive the formula, they want to be thinking of how to be using the formula 1-1, you are going to be stressing yourself. Because any mistake you make, you will miss something. But if you are using the equation of motion, it's already having everything there. No stress. So let's look at question 2. Can I claim? I can claim this part. So when they say pi, you know that pi is 180, 2 pi is 360. And please, I also said that anything about circular motion, always think of what do you have in the normal motion. Anything it is not arithmetic. For example, we know that force is equal to mg, but we know that circular motion force is not tall. Is it not true? I will now say, since this one has to circle, this will be the same as the force. Very simple. When we get angular momentum and dynamics of circular motion, we skip the right bit. So I know to see it. For example, we know that, for example, circle has to do with 360. You know what to do? Then come and put arrow to it. That's the distance of the circle. Because this is the circle and theta and arrow. So for anything to happen, for there to be an angle, there must be presence of radius. So once you have that mindset that the radius must be constant, solves your problem when you're dealing with angular motion. So that is why, if we remember that, all those things will be right when we started with this. So the things I say before the solving, that's where the understanding lies. So please make sure that as you are saying some things, you are noting it down. When you read it, you start adding your own sense to it. You say, okay, this is, and that is how you learn and retain. Because I don't like coming to solve without explaining, so that you don't just, there's this habit students have. Once you are teaching, you solve it, but if you see another question, you have issue. But if you do this one, go through what we've done over and over. Anyhow, you are doing the question, you won't have to. And give me the second one. Another thing I want us to note, see please. Another thing I want us to note is, if I am moving, I have mass. So anything that can be that has matter is mass, is it not good? Okay. So when mass is in motion or horizontal motion or moving horizontally, anyhow, for the fact that it's not rotating, you call it mass, and that mass in motion is called momentum. But the minute mass is in a rotating motion, it's no longer moving linear. However, mass now is rotating, not just moving linear. You now call it inertia. Are you saying it? Yes, because we'll be making use of all those things. So mass that is in motion but rotating is called inertia. Very important.
That's not good.
Inertia. Yes. So textbooks will call this moment of inertia. Yes. I-N-E-R-T-I-A. Yes. Same with I said, when okay, don't worry. See, don't worry. If you did not get it, forget about it. Because we'll still get there. When we start doing, remember I told you that there are three key things we are focusing on when we are treating this circular motion. First is the kinematics of circular motion. Second is the dynamics of circular motion. And then third is the relationship between angular momentum and linear momentum. So when we get there, we now do that. So the minute we finish with angular momentum and linear momentum, our next subtopic will now be rotational dynamics of rigid body. Rotational dynamics of rigid body, which means bodies that are very rigid, that are not supposed to move. That's where we now take this inertia problem. So if you did not get it, don't buy it. I give you the second question. Okay, and so really see now, thank God. Any other thing? There can be cases where they'll ask you to find the tension. Don't worry, we'll still get it. But notice something. Naturally, I think they told us find acceleration. Find this one. Find angular speed. Find angular displacement. No problem. But notice that they have started calling this like linear speed, tangential acceleration, centripetal acceleration. I remember we have a formula for this. Is it not true? Yeah. Particular formulas for this. This is where you can now think of things outside those equations of motion. So using those formulas peculiar to it. But once you see the question as a story, focus on using the equations of motion. But once they now start calling all those individual things like linear speed and tangential acceleration, then you remember that we derive this and we compare this. That's going to use those formulas. Alright, now let's analyze this now. Let's rotating about an axis at the rate. So I'll just, in fact, sometimes you don't know the solution to a question, you write solution. Then your handwriting change, very fine and sharp. Solution will enter. So I'm 0.5 meters. And at a constant angular acceleration of, you see, per second or second square. These things are very important because if they come and give you in per second, that means they want to compete with you. That means you're not going to call it acceleration again. So I have my A to be equal to 4.2 rats per second square. Okay, then at time what? Please pay attention. There's a level of attention you pay and you must understand. Your eyes wide open, ears fast grasping. You just open your eye like this. This one will not pass me. Then, but if you are doing it one with this, you will not follow. Alright, now notice something. I'm giving an object to rotating about an axis. And they get me angular acceleration. They get me time. But notice they did not give me initial velocity. Is it not true? Yes. They did not give me, and notice that when they ask you angular speed, what they're asking is for the final angular speed, not initial angular speed. Are you aware? Hope you are aware. For example, if I tell you, find the velocity, it simply means find whatever velocity after something happens. Yes. But if I tell you find the initial velocity, I'm asking you find me what happened, or should I say the velocity to move to this. That's the initial velocity. So in this case where it is not given, I will take it as my initial velocity is 0. That means somebody wants to ask me how, how? Before you enter the university, if I just say you are in the university, before I just say you are in the university, anybody that hear me will know that okay, yes, I want to go secondary school. Is it not true? Yes. So for that particular velocity to even come to the point of acceleration, it means okay, it started from rest. That is when, and I said it before even this. Once initial velocity is not given, but you are given an acceleration, you take the initial velocity to be 0. Very important, you note it. You can write it down. So this means that I can now have, if I go by my phone, I can now have a W. Let's check if this can work on it. W equals to WO plus AC. Notice that this will be the same thing as saying W equals to initial velocity plus, they get me 4.2. Then time is what? Do you know another thing you will always be checking? One of the things you must be checking is that's your acceleration, if it's in revolution or in radians. The minute it is in revolution, you must convert. So I'm using this one because they will not give you revolution. So with 4.2 times 3 is what? Okay, let me use that. Sorry. Me, I just want to be using A so that when you are reading, you remember, but if you say let's be using alpha, we'll be using alpha. I have for me 4.2 times 3. 12.6. And this is going to be radian per second. You can try and be following. Sometimes I tell my students that the bribe you give yourself in order not to pay attention is you wanting to write. Get the mental picture of that class first. Yes. So that when you are now reading, you're remembering how to respond in class. So I'm gotten now notice that they are asking me angular displacement, not linear displacement. They are asking me angular displacement, not linear. I remember when we said that circular motion always have the linear part and the angular part. I think they asked me the linear displacement here. I will say first of all, S is equal to theta r, which means that this divided by r divided by r. This will be my linear displacement. Are we seeing something? But as they ask me, angular displacement means the angular part. So where is what I'm going to be using is that W is equal to theta over T. Are you seeing it? So if I make theta something of the formula here, what will happen? So first of all, what theta is equal to WC. Is it not true? Yes. I want us to check something. We know that first of all, before we use this principle, we said something. That when we have an equation of motion, you remember that we should stick to first of all using that our equation. Whenever we have a story to the motion question, that we should first of all stick to our equations of motion. Is it not true? So before we think of this, let's check something. I want us to do Theta, there's a formula that we got from that equation of motion. Theta is equal to ut plus, is it not true? Plus half alpha c squared. Is it not true? Yes. Please check for me. Then we also said that b squared is equal to u squared plus 2 alpha theta. So please, looking at these two, which one should we use? And remember, please, this should be W.
Press 1.
Jenny? So let's check something. They give us. Okay, yes. Yes. So if we check this very well, which one should give us a line? We have initial velocity, Jenny, and we have time, and we have acceleration, right? But let's try using the first one. Yes. So I have. Is it confusing? Yes. Okay. So I have theta to be equal to 0 times t, and my t is 3. And I know that anything times 0 will get out. Okay, plus half. Then my acceleration is what? 4.2. Then times t. Please question me. For points for me.
18.9.
Theta is what? So I see. Did you do 9 times 4.2? Then you divided by 2. You got 18.9. And this will be what? It will be in radians. Should you know? I say rats. But please, what? I want us to check something. Okay, this one will be different. Are you sure? So you did W, which is 12.6, then times 3. You got what? That's 7.8. Are you sure? Okay, I believe this should be correct. This one should be more correct. So I'm checking one. Okay, yes. There's no acceleration here. Shall we? Is there any acceleration there? I have W, and I have to go through the acceleration to get that W by multiplying. Yes. So if I use this, it simply means that I'm using W, and there is A here. Then I'm using T. Okay. So this should be more correct. Okay, this should be more correct because I'm having the individual things given to me there. I'm having the acceleration, and I'm having when I will use this, when I will stick to this, I'm only giving the velocity and my time. So I'm sticking to this. I'm giving acceleration. I'm giving initial velocity, I'm giving time, initial velocity. So this much is more correct. Yes. A is equal to what? And you know that formula is for the linear part. Is it not true? W square R. I can do this when they ask me, if they ask me to get the linear acceleration. Do you remember? When we got this W square R is when we are comparing now. When we are saying linear displacement equals to this. Linear velocity equals to this. So linear acceleration, I think they ask me to find linear acceleration now. That's when I can use this. I say W square times R. I'll get it. The same way I did with that first question where I did, okay, we've not even gotten here. It should be here. Let's do it. So here I'll do linear speed is going to be, let's check. You know, the problem is that sometimes we try to prove. We almost confuse ourselves because I was trying to prove this with the other one. But I think in us trying to prove this, we'll confuse ourselves because there's an acceleration here. Alright, linear speed is equal to linear velocity. We have V. When we started, we did V equals to WR. You still remember? Here we said that what you call velocity in kinematics Here we call it W. Then always put our constant, which is R. Do you still remember?
Yes.
But since what we are dealing with is rotating, a body that is rotating. Since what we are dealing with is a body that is rotating, we can actually say, let's say we divide this by R. Divide this by R. What am I going to have? This will cancel the shading. So that I have that W is equal to V over R. Shading? Yes. But notice something. Notice something. I have this already. This question. I have this, but I don't have this. Is it not true? Which means what I'm going to do is just this. And remember when we started that V that V is equal to S over T and is equal to W. You still remember? So that's what I'm doing. I think I was not doing this. I will make this sort of representation. So that means that I'm sticking to it. So what I'm going to simply do is to say V equals to my W is what? 12.6 times my R. 0.45. And I watch for me what you have. 5.6 7. So this equals, and you know that this will be in meter per second. Are you aware? Are you aware that it will be in meter per second? Yes. Please, I almost confuse ourselves. Yes. Please, when they say linear speed, you will remember that linear speed has a relationship with angular speed by that WR. So it simply means that by the time you finish studying your linear speed, the answer should be meter per second. Yes. It's not hard to comprehend. It's not hard to comprehend. Linear, see, they are telling you, when they say something is linear, it means the line path. See what the line path. And I told you when we started that every circular motion has the line path, vertical, the horizontal path, and then the curved path. Yes. So it will be confusion, sir. That's what I wanted to do. It will be confusing us trying to make W a solid of formula. Because if we make this now W solid of formula, it simply means that what we are doing is simply finding the angular part of that linear motion. Are you seeing it? Yes. Because notice I've gotten V here now. Is it not true? And this is a motion on this straight path. This is straight on this. That's the one. So if I put V, then put over R. Now is I'm finding angular motion of a circular body was this linear part of it. You see this? So it is not like the linear speed, you know that this V is all the asking us. It's not hard. However, I want to explain it, but people that want to learn it to learn it. I can't hear you. Can I use theta over time? If I'm using theta over time, that is what I'm looking for is angular velocity or angular speed. When we started, we said it. If I'm doing theta over time, what I'm not doing is actually, which is W. That means that what I'm doing is angular speed. And that is why when I started with that every circular motion has a linear path and an angular path. So if I'm asking angular speed, assuming I have theta in this question, I can, even if you go through this question, like let's say you start thinking about it, whichever way you want to go around, trying to use a lot of things, all the formulas you know, one way you see that you will always be finding yourself having the same answer, making sure you're using the right thing. So angular speed, I think I have theta, that's when I can do theta over time. When they tell me linear speed, I must make sure I'm using it so that my answer will be better. Give me the okay. The next one is tangential acceleration. And I told you that even thank God this one has no confusion. You know that this one has no confusion, Shebi, you know, because all over here, the reason why the others are looking at it is confusing is because it's related to something that relates to something. But this one is just if it's slowing down, if it's too fast. So just like if your fan is starting its movement, you don't think that it's slow. You are seeing the direction. All of a sudden you can't see the direction. Yes. So that is the tangential. Acceleration found in the circular body when it is slowing down or when it's speeding up. That's tangential. And I said that if it's rotating, we consider the path to it and which direction is it going. The path, the straight path to it and which direction is it going. And that straight part of it is what we call the arm. What is moving from. So we say that AC is equal to Notice that sometimes I will explain. I almost put myself in trouble. Why? Because some people will be asking, even if they explain, people will still call you. Yes. I wish maybe in time, years to come, there will be something like a magical app or the when you carry your phone, that they will just come and connect to your head, or put information in your head by force, and it's stored there. You see that you remember, not giving you all those things, whichever topic you want to study. The area. Notice the area, I'm giving A now, so when I find A, check.
Alpha now.
Sorry, let me use your alpha. But see, please, when you are doing this, we don't use alpha, we normally use A. I see it. So I say equals to 4.2 times, they gave me reduce 0.45. This one is very simple. So tangential acceleration, what's here for me? 1.89. Now, please, this is our tangential acceleration. Will it be in meter or radians? It will be in radians per second square. So please have it in mind that the only time we use meter per second square in circular motion is if they ask me linear acceleration. I see it, which is that one that is A equals to W squared R. So if I put value for W, put the value for R, that's where I can now get that. So but outside this, have it in mind that capital value is always okay, the last one. The last one is tangential acceleration. And notice that from this equation right now, you ask me, can we use this? From this equation, we can now get our tangential acceleration. I can say, this is that I have that A equals to W squared as those things we did before, and W is V over R squared. Then this is the center, then V squared over R squared times R. I have V squared over R as my A. So let's substitute. What value did we get for V? But do you know one thing? Do you know how to make this thing become very clear to you? All these things we solve, even the ones we solve with the equations of motion. When you get to now, start trying to use. Remember all the things I said. Angular this one, linear this one. Then start trying to use all those formulas when you do it in value. You see that by the time you do it here, you will get the same answer. Yes, just go through it when you get what C. Alright, so now A is equals to 5.67 all squared all over what? R which is what? 0.45. Is it not true? But please try this for me. Let's check something. If A is equals to W, what's the idea by W? 12.6. Is it to check? Square. N times 0.45. What do you have?
It's giving the same answer. 71.
Okay, it's giving the same answer. 71.442. I want to get this. Well, see, the reason why I'm going to be using this one. The reason why I'm going to be using this one is because I need my answer in radians per second square. Are you seeing it? Yes. So this is going to be 71.442 grams per second. Very There is option A, option B. No, it doesn't. Check and show you where it was. That is that whichever way we solve it, it's giving us the same answer. Is it not? Yes. So how we even check this is to ask ourselves, see, this particular one that is here, this is radians per second, then raised power to Shireen. Yes. See now, then I have my arm, which is what we did. So when we substituted after everything, we got it to be over R. So I don't want to use it, and I don't want to say to be meter per second square, because it's going to be second. But this is the linear acceleration. And whenever they tell me about this linear acceleration, this is what it is. So please, when you get to what you are doing for me. You know the truth. Why is looking as if some things we say is confusing you is because I'm even doing extra. There are some things that I'm not supposed to come and be explaining to you. That's why it looks as if you have so many information. So what you now do is the so many information you have, when you get home, try to put it down, break it down, see how you can come up with certain things that will be useful to you. So it's not a problem. I'm not going to use it. Reason being that this is called linear acceleration. Remember when we compared it? Why for our centripetal acceleration from here we're able to discover this. So he gave us the same answer to show you that we're correct, which is the same thing I'm saying that if you go home, calm down and analyze everything we saw using all those equations one after the other, counting. You see that we're giving you the same answer. Alright, so is that all? Okay, that's all. Okay, so let's go to question 3. Yeah. Are you okay? 347. You want to go home? 347. See, let me tell you. Excuse me, let me ask you. Can you hear me? What is the difference between a soldier and a policeman? What is the difference between a policeman and a soldier? The difference is training. Yes, because you see that the soldier man, even when he wants to run, he remember that, come on, I trained very well. He will stay back. When he wants to collect some kind of money, he will remember the way he was trained. He will say, no, I passed this one. Yes, but you will see, because I don't want to say it because I'm on camera. What? so you will see that, you know, there is a way you will receive this training. And you get used to it. Even when you go to 200 level, 300 level, if a professor comes to shake you with maybe dismissing by 5, 6 or fixing time anyhow, the person will be surprised. And you notice that sometimes when somebody is doing something and that thing is difficult for you, they want to be using the same style. But when they notice that you don't even feel it as anything, then they will be like, okay, and this is not anything to these people. Yes, so let me just calm down. It's as if I'm wasting my time. But see what will happen. See what we'll do. As much as you're going to take the language from home and solve, but we are going to solve it together. Remember that there's a classwork or homework. I gave you a dynamics. And it's submitting on Saturday. So what we will do now is, for the fact that I don't want you to be stressed, let's just analyze the relationship between linear momentum and angular momentum. It's not future. Do you know what they call one way? Human being must adapt. Adaptation is part of your characteristics. See, if you do it, you get used to it. You adapt. See, write on your notebook. You can just write somewhere. We'll still continue with our class works, right? Relationship between linear momentum and angular momentum. If you finish it, you go. Relationship between linear momentum and angular momentum. Relationship between linear momentum and angular momentum. I see, please watch. In linear momentum, we say that linear momentum is the product of mass and velocity. We say that linear momentum is the product of mass and velocity. Have you written that? Yes. Linear momentum is represented with speed, or to call it fast, is the product of mass and velocity. And we say that, we can also say that linear momentum is mass in motion. That's another way to put it. It is mass in motion. It's mass in motion. Now, if I know this, it simply means that whenever a body is moving and there's a body of mass, however it I said linear momentum is the product of mass and velocity. However it is, even if the line corrupt, the line comes down, or if it's going straight, what we are talking about is the momentum, whenever mass is moving. But for example, I have a body of mass or a ball, I play this way, play this way. But the minute I come and tie that ball, for those of you those days that will buy your ball, you leave it under your room. The minute you start doing it like this, is it not true? Sure. The minute you start rotating that particular ball, what you are talking about is an angular momentum. I see it, yes. So notice that at that point when the ball is this way, I'm rotating it. I'm holding it at the end point of the side. But I can have a case whereby I have an object. And this object that I have, let's say I come to the center. Let's say I have a dumbbell now. Dumbbell, for those of you that do try it, you start turning it like this, turning it. Those of you that know how to do all those hand movements, you put it in the center, you're turning it. You see that you are rotating it to the center. It's not it's no longer from the end. It's not from the center. Just like if I have this my marker, or let's say I have this, people that can rotate very well. You see, I'm rotating it from the center. It's different from maybe I'm turning this, which is not possible. So, two things you need to consider is that when you're not talking about angular momentum, you're not talking about the relationship between linear and angular. When you're talking about angular momentum, you are checking the different orientations or the different ways that you can turn that body. Is it at the edge? Or is it at the center? Or is it close to the center? Which way can you rotate it? Which part? That is why you will see some person that will ask you, a body is rotated at the edge or to the edge. Calculate the angular momentum or to the center, or they tell you the sphere or a disc, whatever it is. So what that means is that when you are rotating a body and no longer moving linear, then you no longer call it mass, that you call it inertia. And that when you are talking about any body that is rotating is no longer going to be having velocity, but rather I see it. That is why we now say that angular momentum, which is given by I, is equals to I, the product of inertia and angular velocity. So we say that angular momentum is the product of inertia and angular momentum. Is the product of inertia and angular momentum. Now, please, I want to ask you, do you remember what area is? I said angular momentum is the product of inertia and angular velocity. Did they get? What did I say? Sorry. You know that as a sleep never is it trichotillomania. So maybe you are sleeping and tiredness. It's transparent, not for me. That's why I said the product of inertia and angular velocity. Now that you know this, I want to ask you something. Do you remember that area is given by the vertical axis and the horizontal axis? Is it not? Which means this will be in meter, this will be in meter. That means if this is length, this is length. If this is radius, this is radius. Is it not? Whatever this is. That is why we normally give it that when we progress, we start doing it together. But we normally give it that inertia is given by mr squared. In your physics textbook or in some advanced textbook, you see that they are writing inertia is given by integral of r squared with respect to m. So, you see, once they put this thing, you get confused. Yes. Is it not true? Okay, I should really. Don't worry, we'll not come to this stage. So, for this, our stage, you know that we are taking a small step, there will be no confusion. So, inertia is equal to mr squared. I see this. Simple. I remember that linear momentum is equal to m. Is it not true? Now let's come and replace this I with mr squared. Do you remember that angular momentum is equal to something? Which is what? So this angular momentum. When we did this angular velocity, when we compare velocity, linear velocity to angular velocity, we got something. That V is equal to WR. Is it not? Then that you make R and W such a formula, divide both sides by R. I don't know how you want to do it. But even if you need straight, you take your bath. Be thinking about everything we did, how we did it, so that you master this thing, this concept, you are very related or different. So you see, I'll come and replace this now with V over R. Now notice that this thing, if you times it, This one can easily cancel this. Is it not true? Shall we? Now, which means that this is the same thing as saying if I put MV, bring your arm here. Is it not true? So that linear momentum, angular momentum is equal to MV. In fact, do you know that this thing I did is just to stress myself? Because I've already told you that anything you know in linear, if you are talking about the angular part of it, just come out. Is it not true? Which means that if I know that linear momentum is equal to MV, I can just say angular momentum is equal to MV, put out. Are you seeing it? Yeah. Very simple. So anything that you know that has a linear part, once you're talking about the angular part, just go and put out to it. Very simple. So this thing that we're trying to derive is just to stress ourselves. So if I know that, it simply means that angular momentum is the same thing with linear momentum, just that angular momentum will always come with the constant. Why is it coming with the constant? Because for you to make an angle, there must be a radius. Alright, now I will go back again to that part where we said from Newton's second law, because in Newton's second law, that's where we derive momentum. So from Newton's second law, that's where we derive everything about force. A very powerful formula. He said that the rate of change of momentum is directly proportional to applied force, or the rate of force, or the force applied is directly proportional to the rate of change of momentum. This thing, remember, that F equals mv over c. What do you say, remember? That time we normally come and say v over t is not k, direct acceleration, mk. Is it not? Or we come and say cross multiply ft is equals to mv, and ft is in force. Is it not true?
Yes.
What I will just say is, if that be the case, it simply means that force naturally is equal to mv and here. Notice that is equal to linear momentum. Is it not true? So let me replace this with linear momentum, b over c. I say it? Yes. So which means that force is equal to the ratio of linear momentum and time. So see, force equals to linear momentum and then time. So if I know this, I can still use the same concept and say, okay, from Newton's second law, we know that what we talk about whenever a body is moving, like in straight, be it horizontally, vertically, we're talking about force. But when it's now circle, the force we're talking about is torque. And I told you that torque, so using from this Newton's second law, we said that torque naturally is equal to force times radius. Are you seeing it? And now we know that force is everything here. Is it not? Which gave us P, Chevy? And notice that here, this linear momentum is equal to P. Is it not true? Because F is P. Oh, fine. So that means that I can say T is equal to P over T. That is putting everything about force. Then times R. I see it. Torque, now we say that torque is equal to force and radius. And in fact, I say that torque, that normally you say that force for anybody that is not in a circular motion is called force. But for circular motion, the force stand there is called torque. T-O-R-Q-U-E. So if I know that, I will then say, okay, that means that I can replace what I have for force as P over T. I have it here. Now notice that if you do this is separated with multiplication. Is it not true? So that means that torque is equal to the same as PR over T. Is it not true? And notice that PR is equal to something. Is it not true? Yeah. Which is angular momentum, right? Which means that torque, there can be cases where they give it also, which means that torque is equal to angular momentum over time. Are you seeing it? Yes. So please, what I want you to note from this is simply that there is no difference between circular motion and linear motion. The only difference is just anything you have for circular motion or you have for linear motion. Just if it's in the multiplication part, go and compare it to a constant r. If it's being divided by t, just say that particular thing that you're talking about divided by t. So notice that as I'm talking about torque now, and it has to go with the force of a circle. That means that it will be, instead of doing momentum, it will be angular momentum over time. Why? For force, that is for motion, normal motion, that is straight line or whatever. You know that force is equal to linear momentum over time. So it's the same thing. So if I know that we need to also know, please, we need to also know that it is not every time, it's not every time that we are going to be having our BR. Here we do that. Here that we did angular momentum. The reason that this thing is BR, you see that this? Linear momentum times R. But there can be cases where, since it's an angle, since this radius can be attainable. So let's say a situation whereby this R is at this X. You will see that there will be no need to check let's say if we multiply by this, it will just be at this, that is BR, very simple. Now, you can also have a case whereby this is at vertical. If we check it, don't be checking the angle because the angle is already at the angle vertically. This will be useful. But in a situation whereby this our angle is at this point, or at this point, or at this point, or at this point, we now know that we've come across vectors, you know, and vectors say that if something is not at an angle, it's vertical or horizontal, we do resolution of vectors, right? And remember what I taught you about resolution of vectors. Resolving to the y-axis, which means that this is not the second and say that arrow can also be equal to BR sine theta. So there are cases where you don't have to that's what you say what you say. Yes, I said in fact it's supposed to be something you are used to. You are supposed to be used to it that if something is happening normally, that if let's say I have when we did moment for example, notice that whenever we have our force at 90 degrees, we just say moment equals the first time to particular distance. Is it not true? But the minute you come and see it at an angle, we start trying to resolve it first of all. Which means that the force there will no longer be force times distance, but rather times something of that component, which is that particular force times theta. So that's why I said that it's not every time we have this way. This one is maybe when our arm is at 90 degrees, or maybe at the x-axis, or maybe the arm is at an angle. We are using r sin theta in order to resolve it to a component. Very simple. Remember I told you when we started, even when we did moments, that if it's at the horizontal, it's of no use resolving it. Because that means that if I have a particular distance and it's at the x-axis, that force will simply have to reverse. It's no longer moving. It's no longer moving. So it's simply BR sin theta. No need to resolve it to the x-axis. You use that constant to the moment. It's not hard. And I believe as you start solving questions, it will open up your brain more. So please, what I know now, if you like, be here. I'm saying that we just ran down the class and go. Please, do you remember when you did that momentum? They told you that there's something called elastic position. And in elastic position, you remember? Yes. And you know what we'll do? What we'll do is, since you are tired, you say you gave us this money, right? Yes. What we'll do is that we take it that we stopped at our number 2. That is, yes, that is the questions, the angular motion. Yes. So from our next class, what we are now going to be starting is dynamics of circular motion. So please, all the questions under kinematics of circular motion, go and solve it for me. I will open the group so that we can post our solutions on that group. Then me, I will make a video solving the whole question. You now check your value with my own answer. So what is it today or something? Today is Thursday. Is it not today we are doing a class? So solve it today. I will open the group today. So you post your answers today. Me, I will post my own